Hello guys, I'm back again to represent the Schrödinger time-independent equation. So last time I derived the Schrödinger time-dependent equation, and today I'm here to now give out the time-independent equation. So let me dive into that. So there is it. So the Schrödinger time-independent wave equation, the STIE. So we know that the total energy is equals to kinetic energy plus potential energy. Energy is equals to momentum squared all over 2m, that's 2 times mass, plus v of x. So this is how kinetic energy is presented. Then potential energy is presented by v of x. This equation is under one-dimensional non-relativistic Schrödinger time independent. Should be Schrödinger time independent Schrödinger equation. So should be under what is known as independent. That point should be independent. Then okay, so let's continue. So multiplying by psi, which is the wave function, then again the second method will be general function of psi. So first of all, we'll multiply with psi and give the general function of psi. When we take this particular equation, which is the equation of total energy, multiplied by psi of x, which is now one-dimensional, it will be E psi of x is equals to momentum squared all over 2m psi of x plus v of x psi of x, and let's denote that as equation 1. So this will be marked as equation 1. Then the general function of psi of x will be now psi of x is equals to exponential I into k of x minus wt. Let's mark that as equation 2. Then continuing, differentiating equation 2 with respect to x. So differentiating this particular equation with respect to x twice, then we'll be having delta squared psi of x. The same method that I used in differentiating the Schrödinger time dependent is the same way that I've differentiated this with. So delta squared psi of x all over delta x squared is equals to I squared k squared times exponential I into k x minus omega t I squared k squared multiplied, which is equals to I squared k squared multiplied by omega x. Then continuing, we know that k is equals to 2 pi all over lambda, which is equals to 2 pi p all over h, which lambda is equals to Planck's constant all over p, or all over momentum. So we know that k from the Schrödinger time dependent, we know that k can also be written in this manner. So k being that is momentum all over h bar, then we can have delta squared psi of x all over delta x squared is equals to negative momentum squared all over h bar squared psi of x, which we know that this one, which is momentum squared psi of x, is now equals to this when we put the momentum psi of x as the subject of the formula. Then continuing, putting equation 3 in equation 1, we'll be having total energy is equals to, that's energy psi of x, is equals to negative h bar squared delta squared psi of x. So it should be negative h bar squared all over 2m delta squared psi of x all over delta x squared plus v of x psi of x as equation 4. So let that be equation 4. Then continuing, we'll be having energy psi of x minus v of x psi of x plus h bar squared all over 2m delta squared psi of x all over delta x squared is equals to 0. Then the ST IDE, that's the Schrödinger time independent equation, will be now delta squared psi of x over delta x squared plus 2m over h bar squared into energy minus v of x close the bracket multiplied by psi of x is equals to 0. So that's the Schrödinger time independent equation. Thank you for watching and stay tuned as I'll be showing so many questions to be derived. Thank you very much.